Hello, this is Jack Jackson. In this video, we're going to be looking at a t-distribution versus a z-distribution. Now, the first point I want to make is to remember that anytime we use any statistical inference procedure, such as a z-interval or a z-test or anything like that, we must first check that the conditions that make the procedure work are satisfied. If the conditions are met, we can be as confident, at least as confident as indicated by the confidence level 1 minus alpha, with our conclusions. But if the required conditions are not met, if the test is not valid, and any conclusions from it are meaningless. Okay, so let's just review what conditions are needed for computing a z-test or z-interval. The first is that both z-intervals and z-tests are inferences about the mean of a population. We're finding the center as defined by the mean. In a z-interval, we're constructing a confidence interval estimate of the unknown mean of the population. In a z-test, the one sample version at least, we're performing a test of hypotheses, comparing a sample mean to a hypothesized population mean. This is a very good situation that we're using all the time. It's very, very common, probably one of the most common types of intervals and tests, probably the most common, with proportions coming in as maybe a close second. And so this is a very realistic situation. The distribution of sample means has to be at least approximately normal. This is going to be satisfied if any one of the following hold. The distribution of individual measurements is normal or very nearly so. Even for a small sample size, that works. If the distribution of individuals is unimodal, free of outliers, and not heavily skewed, and I'm going to say, I'm just throw an arbitrary number there and there, around 15 or bigger, then that's going to be good enough to be approximately normal for the distribution of sample means. And if the sample size is greater than 30 for nearly any distribution of individuals, then the distribution of sample means is approximately normal. And this comes from the central limit theorem, which is really what makes all of this work. And the last condition is that the population standard deviation sigma is known. That's the standard deviation of the individual measurements. Now, one of these conditions is not like the others, and that is that the population standard deviation is known. So notice, in order to use a z-test or z-interval, the population standard deviation sigma must be known. And while the other conditions are realistic, reasonable, and often met, this condition is none of these things. It is highly unlikely that we will know the population standard deviation with any degree of certainty. Now, so why did I use a z-interval and z-test to introduce the concepts in those previous videos in this playlist? Well, they were used to introduce the ideas of confidence intervals and hypothesis tests because I think that they're the easiest to understand and have the least amount of details to go through before we get to the conclusions of the basic setups. And they're all based on a normal distribution, which we're very familiar with at this point in the course. However, z-tests and z-intervals only apply to basically an almost non-existent real-world scenario. So the question now is, how do we adjust our methods to fix this problem that the population standard deviation is unknown? We don't know the standard deviation of the population, but we've taken a sample. Oh, wait a minute. I know what we could do. We could take the sample standard deviation, and that's exactly what we do. We use the sample standard deviation of the sample that we've taken to approximate the population standard deviation. Now remember that the foundation of z-tests and z-intervals, that the test statistics from samples are really z-scores of sample means, and they have a sampling distribution which follows a standard normal distribution of z-scores, sometimes called a z-distribution. And so the test statistic that we're looking at is x bar minus mu over sigma over the square root of n, and the sampling distribution for that or of those z-scores is what we call a z-distribution. That's a standard normal distribution. Now, if we replace the sigma by the s, the population standard deviation, by the sample standard deviation, then this new sampling distribution here is not quite a standard normal anymore. It's off just a little bit. And so the distribution that this follows we call a t-distribution with n minus 1 degrees of freedom. So when sigma is replaced by s, z is replaced by t. Now we've looked at t-distributions before, but we will review these some in our next video. Now let's review one more time the conditions used to a z-test or z-interval versus a t-test or t-interval. Z and t, either one, we're performing inferences about means of a population. If it's a z-interval or t-interval, we're constructing a confidence interval estimate of an unknown mean of a population. A z-test or t-test, one sample version at least, we're performing a test of hypotheses comparing a sample mean to hypothesized population mean. The z and the t of the distribution of sample means is at least approximately normal. If the distribution of individuals is normal or nearly so, even for a small sample size, that works. If it's greater than 30 for any distribution of individuals, that's probably going to work okay. And if it's kind of unimodal, maybe a little bit mound-shaped, free of outliers, not heavily skewed, you can probably get by with a some sample size between, a real small and 30, so maybe 15-ish. But here's the decision. Those two things are exactly the same for z or t. What's different? Use z interval or z-test if the standard deviation of the population sigma is known. Use the t-test or t-interval if the population standard deviation sigma is unknown. Now, for large sample sizes, n greater than 30, there is little difference in the appropriate t-distribution with n minus 1 degrees of freedom and the standard normal distribution. So some people like to use the z-test and z-interval if the sample size is greater than 30, and then they just use s in place of sigma and just pretend it's sigma. However, I think that the calculation that we perform, particularly with calculators, is just as easy with the t-test as it is with the z-test. The answer is more accurate with the t-test if sigma is unknown. And the decision of which one to use, a t or z, is easier to make and easier to remember if we only base it on whether or not sigma is known. So in my classes, we will always use the t-test and t-interval for inferences about means if the sample size, regardless of the sample size, if the standard deviation of the population is unknown. If the standard deviation of the population is known, then we'll use the z-test or z-interval as appropriate. Now remember this normality assumption. I've already gone over this a couple of times. Here I've phrased it a slightly different way, but saying the same thing. If n is greater than 30 for any distribution of individuals, n greater than 15 for distributions that are unimodal, nearly symmetric, short-tailed, and without outliers, or n less than 16 if the distribution of individuals is nearly normal. What we're looking at is mound-shaped, unimodal, nearly symmetric, short-tailed, without outliers. If any of those conditions are met, then the distribution of sample means is approximately normal by the central limit theorem. A t-test is considered to be what we call robust with respect to the normality assumption. And what this means is that it works pretty well even if the data deviates a little from the normal distribution and the sample size is a bit small. And it still works pretty good. That's why we got these kind of fuzzy kind of conditions here. But however, if you have very small sample size taken from a distinctly non-normal distribution, particularly things that can mess it up are bimodal, highly skewed, and outliers. Okay, if it has some of those things, or especially if it has all of those, then you're dealing with a small sample size. That's not enough to assume that the x-bars are distributed normally. So we have to use a different kind of test. Okay, and those kind of tests are called non-parametric tests. And typically in my first class in statistics, I don't do too many of those. Hopefully, maybe someday I'll add some videos about non-parametric tests, but probably not right away. So, problems involving inferences about means when the sample size is unknown. no, not the sample size is unknown. What I should have said is the population standard deviation is unknown. Use the t-test for hypothesis testing and the t-interval for confidence intervals for the mean. The interpretation and execution of these problems is exactly the same as with the standard normal z-test and z-intervals, with some very straightforward substitutions that I'm going to go over on the next slide. Now this slide is very busy. It's got lots of formulas and things on here, but it summarizes all of this together in a very easy to follow correspondence. So on the left side we have the z-test and z-interval. On the right side we have the t-test and t-interval. The left side reviews all the formulas that we came up with in our previous sets of videos about z-test and z-interval, and the right side you see how you change those formulas. Everything's very straightforward the way it's changed. Anytime you use the population standard deviation, which is known over here in the z-test, you use sigma. The corresponding thing in the t-test, since sigma is unknown, you use the sample standard deviation s. So sigma is replaced by s. When you do that, the z star test statistic over here, x bar minus mu over sigma divided by square root of n, becomes x bar minus mu over s divided by square root of n. That becomes the t star test statistic over here. The distribution of such statistics is a normal, standard normal, or z distribution on the left. On the right, the distribution of these t statistics is a t distribution with n minus 1 degrees of freedom. The confidence interval in both cases is a confidence interval for the mean, and these distributions are symmetric, so the mean is smack dab right in the midpoint of the interval, and the interval is just x bar minus e to x bar plus e in both cases. The difference is how we find e, but again, it's extremely similar. The margin of error we worked out for a z-interval is sigma, or the sigma of the x's, or just sigma, divided by square root of n times the inverse norm of 1 minus alpha over 2. That translates over here to e is s over square root of n times the inverse t of 1 minus alpha over 2 times, or comma, n minus 1. The sample size over here on the z confidence interval, take the same formula that we just had for margin of error, solve it for n, and we get n equals inverse norm of 1 minus alpha over 2 times sigma of the x's divided by e, and then square the whole thing. And of course, remember, you're going to round up there. The corresponding formula over for sample size in the t-test, or t-interval, is n equals inverse t of 1 minus alpha over 2, n minus 1 degrees of freedom, times s divided by e, and then square it. There's a couple problems with this formula. We have to actually take a sample. The whole point here is to use n to decide how big a sample you want to take. We have to actually take a sample to get an s value. And the other problem is this is not truly solved for n, because we need to know the sample size in order to know the degrees of freedom here. So this is a little problematic. I'll show you how to get around that problem a little bit later on. But for now, you can kind of see that at least this is a corresponding formula. Now, when it gets to hypothesis testing, we have three subcases. We can do left-tailed, right-tailed, or two-tailed test. In each case, we have critical value or values in the two-tailed version, and we have p-values. So we can use the critical value approach or the p-value approach. So in the left-tailed critical values, the critical value is a boundary of our critical region, which is going to have area alpha. All of the area is in one piece to the left of the critical value. So that's inverse norm of alpha, comma 0, 1 will give you the z-score, the z-value from the standard normal curve, which is the boundary of that critical region, which is our critical value c. Remember, inverse norm, you put in alpha. This is what is the area under the PDF to the left of c. In other words, the probability of getting a z-score that's less than c. Okay, at least under the null hypothesis being true. The corresponding thing over here for the t is just inverse t of alpha n minus 1. If you want to find the p-value, remember in general the p-value is the probability of getting a sample as extreme or more extreme than the one that you got. In this case, extreme means further to the left, or the same as the one you have, Z star. So what we're doing is just the probability to the left of Z star, which is given by normal CDF. Well, it should say negative infinity to Z star, mu 0, standard deviation 1. But we've seen before we can replace, instead of negative infinity, we can just use negative 10 for standard normal, and it's not going to affect the digits on a calculator. Over a t distribution has a little bit wider graphs, smaller standard deviation, so I need to use a little bit smaller number in place of negative infinity here, but negative 100 works pretty well, kind of regardless of the sample size. So the corresponding p-value there is t CDF negative 100 to t star comma n minus 1. If it's right-tailed, then the critical region is on the right of the C value, so the probability to the right of C is alpha. Sometimes that's called Z sub alpha, where the subscript is the probability to the right. I'm just going to cut to the chase and use the calculator notation here. C is the inverse norm of 1 minus alpha, which is the probability to the left of C, comma 0, 1. So C equals inverse norm 1 minus alpha 0, 1 for the Z test when it's right-tailed. And the corresponding thing for the T is C equals inverse T of 1 minus alpha comma n minus 1. The p-value is normal CDF from Z star to infinity, but we'll use 10, 0, 1. And the corresponding thing over here for the T is the p-value is T CDF from T star to 100 comma n minus 1. For two-tailed test, then it's a little bit different because you have to take that probability of making a type 1 error, that is alpha, and instead of all of it being, in one region, we have to split it into two regions, each having a probability, that is an area under the PDF curve, of 1/2 of alpha. So you have two regions and two boundary points. The critical value for the lower region, the boundary, is going to be inverse norm of alpha over 2, comma 0, 1, because the probability to the left is alpha over 2. Corresponding thing in T is critical value for the lower part is inverse T of alpha over 2, comma n minus 1. On the left, that's the left endpoint, left boundary point of our critical region. The upper region has a critical value, which is its boundary, of inverse norm of 1 minus alpha over 2, 0, 1. And because a standard normal curve is symmetric about the origin, about 0, it turns out that the lower confidence level and the lower critical value and the upper critical value are just opposites of each other. And that is true over here in the T as well. The T is also centered at 0 and is symmetric. So these critical values turn out to be opposites of each other. One way you could do it is the critical value for the upper one is inverse T of 1 minus alpha over 2 n minus 1. Or basically you can do just one of these inverse T's and then just flip the sign and you've got the other one. Now if you're going to use the p-value approach, then the p-value is 2 times normal CDF from Z star to 10, 0, 1 when the Z is to the right of 0, the right of the mean. So you're getting a sample with the sample mean bigger than the hypothesized mean. And if it's to the left, you want to find your p-value as a area of a region to the left, which would be 2 times normal CDF of negative 10, comma Z star 0, 1. Well, these correspond to T when these things over here in the T, when T star is greater than 0, we get 2 times T CDF of T star to 100 n minus 1, or when T star is to the left of 0, in other words negative, we do P equals 2 times T CDF negative 100 times comma T star comma n minus 1. Notice we have to double it because the p-value is only going to give you half of the probability we want. Put the two together, you're going to get alpha. So now what I'm going to do here is remind you that the left side is the z interval and test, the right side is the t interval and test, and you can see these going back and forth from one to the next as we move from z to t. Now here's the exact same information from the previous slide blown up, and you see on the left the information for the t interval and on the right for the t test. But it's exactly the same thing that we just went over. And so now in the next few videos we're going to put this to work to compute some t intervals and t tests. But before we do that, we're going to go into our next video where we actually go back to a t distribution, which we've looked at before, and just review what the characteristics of the graph are and how to do, on a calculator at least, how to do computations of probabilities and inverse probabilities from a t distribution. So that will be our next video.